Good morning, Avalon, and welcome to Saxon Algebra 1, Lesson 61. This is going to be the first one of these that I'm recording, so hopefully it goes well. Alright, Lesson 61. Lesson 61 is all about numbers, different types of numbers, and how they relate to each other. We've talked about sets before. A set is just a collection of numbers, the same way that, like a Lego set is a collection of Lego bricks. It doesn't matter the order that the things in the set are in. Usually we'll list them in numerical order to help us keep track of them, but they don't have to be. And it's not a different set if we rearrange them. The way that we indicate a set is we put it in the curly brackets. So, like A, set A, is this group of numbers, 1, 2, 3, and 4. We could have another set B, again in the curly brackets. B only has 2 and 3 in it. When we talk about sets, some sets are larger than others. Both of these sets are finite sets. They have an end to them, from the Latin finis, meaning an end, finitus, having an end. You can also have infinite sets, and we'll talk about some of those in a minute. So some sets are smaller than others. Some of them are actually parts of other sets. So in this example, B, the only elements or members of set B are 2 and 3. And set A has the members 1, 2, 3, and 4. So since all the members of set B are also in set A, we can say that B is a subset of A. And this is how we write it. We use this sort of curved less than sign almost. It's not a C. And B is a subset of A. A, on the other hand, is not a subset of B because A has 1 and 4 in it, which are not members of B. Two sets that are the same, that are identical to each other, they're both subsets of each other. Alright, so now we'll get to the new things about sets and different groups of numbers that we have for this lesson. The first one is the empty set or the null set. This is a group of numbers that has nothing in it. It's empty, just like the name. Null, from Latin nullus, meaning none. Two ways we can write it. Either curly brackets with nothing in them, or we can use the 0 symbol with a slash through it. And that means, again, nothing. There's just nothing in the set. It's empty. The empty set is a subset of every other set because all of the members in it, it doesn't have any. It's a subgroup of any other group of numbers. Alright, now to how do we fit together the things that we know about sets and some of the things that we've learned about numbers so far in this class. We've learned about a whole different number of types of numbers, and we're going to talk a little bit about how they relate to each other. Each one of these is in fact a set of numbers. The biggest one is the real numbers. This is any number that you can think of. You know, whether it's something like 5, negative 78, 1,003.1, or 4 pi over 2. Those are all real numbers. The only numbers that aren't real numbers are what we call imaginary numbers. We're not going to deal with those in this course. So any number that we have is a real number. We use this symbol. It's like a fancy R to indicate the set of real numbers. So the same way that we used A to indicate this set up here, and B to indicate this set over here. Anytime we use this symbol, that means the set of all real numbers, all of them. And of course there's an infinite number of them, so it's what we call an infinite set. Now, among real numbers, we can divide all real numbers into two types, either rational or irrational numbers. Rational numbers, let's take a look at the word there. It's from Latin, rationalis, and it's related to our word ratio. A rational number is a number that we can express using a ratio or a fraction. Remember ratios, fractions, we talked about how we can set up ratio problems as fractions and all that. So anything we can express as a fraction is a rational number. So that's going to mean any integer, 1, 2, 3, because we can express those as 1 over 1, 2 over 1, 6 over 2. We can express those all as fractions. Again, any decimal that ends is going to be a rational number, so 0.5, we could write that as 5 over 10, we could write that as 1 over 2, negative numbers are rational numbers also, assuming that they can be expressed as a negative fraction. Irrational numbers are numbers that we can't express as a fraction. The most familiar one to you guys is probably going to be pi. There's no way to write pi using using a fraction. Sometimes you see it as 22 over 7, but really that's an approximation. It's not actually 22 over 7. It's this, and if you see it written out as a decimal, 3.141592653588979. And it goes on and on and on and on. There's no pattern to it. Those are irrational numbers. And again, we're not going to be dealing so much with irrational numbers right now. We'll get into them a little bit later with square roots and those kinds of things. But rational means you could express it as a ratio, as a fraction. All right, within rational numbers, another group of numbers we've talked about, integers, from the Latin integer, meaning whole. These are whole numbers, not in the same way that we talk about these as being whole numbers, because it also includes negatives. So anything that doesn't have a decimal or a fractional part, and is either positive or negative or 0, these are integers. We have a special symbol for the set of integers also. It's this fancy Z, from the German word Zahl, which means number. And you'll notice that this set, I'm able to write it out, but I've got these dots on both ends because it goes forever to the negatives and forever to the positives also. This is another infinite set. There are an infinite number of integers that exist. Within the integers, we can get more specific. We talk about the set of whole numbers. We'll indicate that using W. And the whole numbers are the integers without the negative numbers. So starting at 0 and going up, those are whole numbers. You'll notice again the 3 dots at the end indicating that it goes on forever in that direction. And then we have another subset within that, the natural numbers, or you might know them as the counting numbers, which are the whole numbers except for 0. So starting at 1 and then all the integers above that. All right. Now we're going to take a look at a visual here, which is in the textbook also, but I'll set it up on the board, which can give you a visual here of how these different sets of numbers relate to each other. Alright, so now I've got a visual up here for how these sets of numbers relate to each other. On the left side of the board here, if you imagine that whole side of the board is rational numbers. Again, not worrying so much about irrational numbers or imaginary numbers right now. But the rational numbers, which are the ones that we're really going to be mostly concerned with, that's a large group of number. Remember, that's going to include fractions, it's going to include decimals, things like that. Integers are a subset of those. Right? It's a smaller group. It's not all of the rational numbers, but it is a group within there. There are no integers that are not rational numbers. Anything that is an integer, by definition, you can write it as a fraction of some number over 1. Whole numbers, again, are a subset of integers because it's some of the integers, but not all of them. There are no numbers in the whole numbers set that are not also integers because the whole numbers are integers except for the negative ones. And again, natural numbers is a subset of whole numbers because it's our whole numbers except for 0. So anything that's a natural number is also a whole number, is also an integer, is also a rational number, and is also a real number. All of these, they fit inside each other like those Russian nesting dolls. We can represent this using mathematical symbols like this. So you see up here, natural numbers are a subset of whole numbers, and that's how we can read that. So the N stands for natural numbers, W stands for whole numbers, and then we've got the subset sign. Whole numbers are a subset of integers. Remember that Z standing for the German word Zahl, meaning integer. And then again, our integers are a subset of the real numbers, the fancy Z for the integers and the fancy R for the real numbers. So anything that's a member of one of these groups is also then by definition a member of all the larger groups. So something that's a whole number is also an integer and is also a rational number. Not necessarily the other way though. You could have, because there are whole numbers, where there's one whole number which is not a natural number, namely 0. And there are lots of integers. All the negative integers are not whole numbers. But anything that's a member of one of these smaller sets is also then a member of all of the sets that are larger. Alright, I'm going to keep doing my virtual office hours on the regular time and the same Google Hangout link that I sent the first time. Let me know if you have questions, but otherwise it'll be the evens for this problem set. See you guys soon. Don't skip leg day.